Hello, hello, hello. Welcome to students. I am Captain Raila Sanjeev. Welcome to online classes from Department of Chemistry, Government Degree College, Peddapalli. In the last class, we learned about synthesis and electrophilic substitution reactions of pyridine. Today we are going to discuss about other chemical properties of pyridine. Now, first we will discuss electrophilic substitution reaction. Another example, the last example is halogenation reaction. In the halogenation reaction, here pyridine on reaction with the chlorine and the bromine. We are observing pyridine on reaction with the chlorine in presence of AlCl3, heat the reaction mixture. Generally, it gives 3-chloropyridine. Why the 3 substituent we are getting? Yesterday we discussed clearly with the mechanism that a particular 3 substituent are contributing resonance structures. All the resonance structures, they don't have positive charge on the heteroatom, that particular nitrogen atom. Because that, due to that reason, generally pyridine undergoes electrophilic substitution reactions. On third place, it gives more yield 3 third substituted product. Pyridine on reaction with this chlorine, 3-chloropyridine. Pyridine on reaction with the bromine will get a 3-bromopyridine. Okay, 3-bromopyridine is produced in good yield by the action of bromine in presence of oleum. This is the right side. We are representing this bromine in presence of oleum. Heat the reaction mixture. We are getting 3-bromopyridine. The left hand side, 3-chloropyridine can be produced by chlorination in the presence of aluminum chloride, AlCl3. Heat the reaction mixture, will get 3-chloropyridine. This is about halogenation reaction. In these two reactions, we observe three substituted product is the major product in these two reactions. Now let us go to very important reaction, another type of reaction. Pyridine undergoes nucleophilic substitution reaction. Why the pyridine undergoes nucleophilic substitution reaction? At the second position we'll discuss, C2 position. Generally attacks on nucleophile on C2 position. What is the reason? We'll discuss. Okay, based on these reactions. Here we are representing C3 contributing resonance structures and C2 contributing resonance structures. Here I did not mention that fourth position also, C4 position is also possible, but when we compare with the C2, it may not obtain the C4th product, but C4th substitution is also possible. C2, C3, C4th, but here in this slide we cannot mention that C4th structures. That is also possible. Okay, step by step we will discuss clearly. Uh, in this, particularly in this pyridine, the low density electron density at second and fourth positions is responsible for nucleophilic substitution reactions. Generally, second, just now I mentioned C fourth is also possible. C fourth position and C second position. These two positions are low electron density positions on the cyclic pyridine ring. C2, this is the C2 position and C4th position. These two positions are low electron density positions because the nucleophile negative charged species automatically attacks on these two positions. In between, the second position is preferable. What is the reason? We will discuss. But second and third, fourth positions are low density positions. In presence of strong nucleophile, such as amide nucleophile or alkyl anions are minus nucleophile or phenyl anion. Phenyl anion we can represent Ar minus or in some cases pH minus. We can represent like that. All these type of nucleophiles, strong nucleophiles, exhibits nucleophilic substitution reactions on pyridine ring very easily, very easily. Here C fourth position I did not mention. C2 and C fourth positions are preferable positions on this particular ring. Here C3 is also possible, but C3 is not stable. Why? We will discuss. Here, if the nucleophile attacks on C3, in that case this pi bonded electron shifted to C2 side. That C2 gets negative here. C2 gets negative. Is it clear? That particular nucleophile negative charged species attacks on C3 position here. This is the one of the contributing resonance structure. This negative charge, if shifted to this side, immediately cleavage of pi bond, C6 carbon gets negative here, negative. Okay. From this is another type of resonance structure, second type of resonance structure. From this, here, if the negative charged electrons shifted to this side, immediately cleavage of this particular pi bond, C4th and C, in between C4th and C5th pi bond cleavage takes place. Here, C4th carbon gets negative. This is the situation. Immediately we'll get this type of resonance structure. Resonance structure. Is it clear? From this we can write here, if the negative charge shifted to this side, loss of H minus hydride ion, H minus will get a final product nucleophilic substituted at third place substituted product. Is it clear? These are the contributing resonance structures from C3 position. Attack of electrophile on C3 position. Here, please observe C2. C2. As shown, C4 is also same. C2. Please observe. If the nucleophile negative charged species attacks on this low density position, here the pi bond may be shifted to C3 side. In that case, the C3 carbon gets negative, nucleophile automatically bonded with the C2 carbon. This is the one of the resonance structure from C2 attack. From this, here the negative charge may be shifted to this side. These pi bonded electrons shifted to C5th carbon. C5th carbon gets negative here. The remaining same. Here new pi bond generated in between C3 and C4. New pi bond generated, negative charge on C5th carbon. This is the second type of resonance structure for C2 attack. From this, please observe, if the negative charged electron shifted to this side, cleavage of pi bond in between C6th and heteroatom. In this case, the electron density increases on heteroatom here. The electron density increases. The electron density is more on heteroatom. That heteroatom nitrogen atom gets negative here. Negative. From this we can write here, if the negative charge shifted to this side, loss of H minus, we will get a final product. Final product. These are the contributing resonance structures from C2 attack. Attack of electrophile on C2 position, we are getting the same number of resonance structures as compared with the C3 and C4. But please observe all these structures. Which one is more stable, which is less stable, what is the reason, we'll discuss once again. Here, attack on second position. Attack on second position gives more stable intermediate containing negative charge on nitrogen atom. Negative charge on nitrogen atom. Thus, the pyridine contributing resonance structures are very stable. Here please observe, generally the nitrogen atom is highly electronegative atom. It holds negative charge on nitrogen. In that case, the structures are more stable. Here, when we go to C2, attack of electronucleophile on C2 position gives various structures. Here, please observe the third structure. It contains negative charge on nitrogen, especially stable structures from C2 attack. C2 attack. Here, at the same time, please observe on attack of electrophile on C3 position. Here, please observe the first, second, and third. In all these structures, there is no negative charge on heteroatom. There is no negative charge on heteroatom, because that these structures, when we compare with the C2 attack, these are less stable structures. Is it clear? In C4 attack also, it gives negative charged on nitrogen atom structures. But when we compare with C2 and C4, when we compare with C2 and C4, C2 attack is more preferable. The reason means, here please observe, the second position here, second place, nitrogen. The second position is directly linked with the nitrogen atom. This is the reason. The second position, when we compare with fourth position, fourth is very distance to heteroatom. Here, second position, it is directly linked with the heteroatom, that particular nitrogen atom. High electron deficiency will be uh, there. Nucleophilic substitution occurs at a second position easily. That C2 position is directly linked with the heteroatom. Heteroatom, nitrogen atom, is a more electronegative atom, attract electrons from C2. On C2 there is a creation of, there is a electron deficiency, because that the nucleophile negative charged species attacks on that particular C2 position very easily. This is the clear information about nucleophilic substitution reactions. This nucleophilic substitution reactions generally preferable on second position. Now let us go to one of the example, very good example for nucleophilic substitution reaction. It is a well-noted example. Please remember, all the students. It is very important in this pyridine nucleophilic substitution reaction. It is very important in examinations, also in entrance exams, and academic exams. It is a repeated question. The name reaction, it is a Hcc reaction. Hcc reaction, one of the suitable example for nucleophilic substitution reaction. Reaction of pyridine with sodamide at a high temperature gives 2-amino-pyridine. Here, pyridine 2-amine. We can also tell like that. Pyridine 2-amine. Here, please observe pyridine on reaction with the sodamide. Sodamide in presence of ammonia, NH3. We are using in presence of ammonia. Heat the reaction mixture. This particular nucleophile, amide nucleophile, NH2 minus, here cleavage like this, Na plus and NH2 minus. NH2 minus nucleophile attacks on C2 position. Just now we discussed what is the why the C2 position is preferable. amide NH2 minus attacks on second position, we'll get 2-amino pyridine. Is it clear? Pyridine. This is the major product. Now, in this reaction, we will observe mechanism part of this particular reaction. Here, first in the mechanism, first step is first this particular sodamide cleavages. Sodamide NaNH2. After cleavage, it gives Na plus and NH2 minus amide ion, sodium cation and amide anion. This particular amide anion NH2 minus amide anion here attacking on this side C6, actually we can tell C2. If attacks on C2 position, amide anion, here this side it is mentioned NH2 and H is also there. H is also there. Attack of amide ion on second position gives three contributing resonance structures. After attacking of this amide ion, we will get three contributing resonance structures. Structures will get like this. Here, if the negative charge shifted to this side, these pi bond cleavages, this C3 carbon gets negative in that case. One of the resonance structure. After that, if the negative charge shifted to this side, pi bond cleavages, that C5th carbon gets negative, like that. Like that, we can write uh, three types, three contributing resonance structures from this intermediate, because that this intermediate is more stable resonance structure. From this intermediate, what happened? In presence of ammonia, we are using extra. In presence of ammonia generally cleavage like this: NH2 bond H, NH2 bond H. This NH2 bond H, that sigma bonded electrons attracted by nitrogen. In that case, again produces NH2 minus amide ion and H plus ion. It gives H plus ion. That particular H plus ion bonded with a H minus. This H minus ion loses from this cyclic ring here. After shifting of this negative, loss of H minus. This H minus, in presence of ammonia, we are using extra we are using as a catalyst. That particular H plus bonds with H minus, finally H2, loss of H2. Is it clear? Finally, we are getting 2-amino pyridine. 2-amino pyridine is the product in this Hcc reaction. It is very important reaction, suitable example for nucleophilic substitution reaction. Another example is also there for nucleophilic substitution reaction. Arylation. Arylation. If same pyridine ring on reaction with the phenyl lithium. Pyridine ring on reaction with the phenyl lithium. In phenyl lithium, phenyl ring delta negative charge, lithium delta positive. Positive. A breakage like this. Lithium plus and a phenyl ring or aryl ring negative. That particular phenyl pH minus or Ar minus nucleophile, pH minus nucleophile attacks on pyridine ring. Pyridine ring. In that case, to forms aryl pyridine, through aryl pyridine. This is also one of the suitable example for nucleophilic substitution reaction. Arylation, aryl substitution on that particular second position. In this case, the byproduct is lithium hydride. Here, sodium hydride is the byproduct. Another example for nucleophilic substitution reaction, same pyridine ring on reaction with the N-butyl lithium. N-butyl lithium. N-butyl lithium, in that particular compound, N-butyl delta positive charged, lithium delta negative. Breakage of this particular butyl lithium sigma bond, it gives butyl N-butyl minus nucleophile and lithium plus. That particular N-butyl minus nucleophile automatically attacks on second position of the pyridine ring. In that case, we'll get N 2 N-butyl pyridine. 2 N-butyl pyridine. This is also one of the example for nucleophilic substitution reaction. This reaction is on second position we are substituting alkyl group because it is named as alkylation. Arylation, just now we discussed, and alkylation. Alkyl, butyl, N-butyl normal chain substituting on second position of the pyridine cyclic ring. In this case, byproduct is lithium hydride. Lithium hydride. Is it clear? Is it clear, all of you? For this nucleophilic substitution reaction, another important reaction is also there. Reaction with the potassium hydroxide. Reaction with the potassium hydroxide, KOH, strong base. If the reaction with the potassium hydroxide, strong base, what happened? Please observe. Pyridine on reaction with potassium hydroxide, heat the reaction mixture at 300 degree centigrade. 300 degree centigrade. Here, potassium from potassium hydroxide, K plus and OH minus. Here also OH minus hydroxy nucleophile. OH minus nucleophile generally attacks on second position. That OH minus nucleophile attacks on second position, gives 2-hydroxy pyridine. 2-hydroxypyridine. Pyridine on reaction with the potassium hydroxide gives 2-hydroxypyridine. This particular 2-hydroxypyridine is a less stable compound. For that purpose, it changes internally to molds more stable structure, more stable its tautomer. What happened in this hydroxy group, hydrogen, that OH bond shifted to um, O negative side, that pi bond shifted to heteroatom. That particular H plus ion migrated to heteroatom, nitrogen, migrated to heteroatom on nitrogen. In that case, the structure, the final structure after migrating of H plus ion, after shifting of that particular H plus ion, will get 2 pyridone, 2 pyridone structure. 2 pyridone is this tautomeric structure is more stable when compared with the 2-hydroxypyridine. In this particular potassium hydroxide reaction with the potassium hydroxide, we are getting 2-hydroxypyridine, but this structure may be changed as more stable resonance form. Is it clear? This is also one of the suitable example for nucleophilic substitution reaction. Nucleophilic substitution reactions. These are all the different examples. So many extra examples we are giving for this nucleophilic substitution reaction. Here another important reaction. Pyridine as nucleophilic catalyst. Pyridine acted as nucleophilic catalyst. Here please observe in the reaction part. Used as a catalyst for acylating phenols, alcohols and amines using acyl chlorides or anhydrides. Here please observe in the reaction part. Alcohols on reaction with the acyl chloride. Here acyl chloride in presence of this pyridine catalyst. Here pyridine acted as a catalyst, pyridine catalyst to forms ester. In this reaction, pyridine acted as a nucleophilic catalyst. In what way? Please observe in the reaction mechanism part. Here, acyl chloride, that acyl carbonyl carbon, pyridine pair of electron, that heteroatom electrons bonds with the carbonyl carbon. Here breakage of halogen chlorine, breakage of halogen chlorine to forms reactive trigonal intermediate. Reactive trigonal intermediate. Okay. Now let us go to on reaction with the second starting material, that is alcohol. Another starting material, alcohol. In the first case, we used acyl chloride. Next, in the second step, we are using alcohol. Alcohol. Here, ROH, alcohol. That OH, oxygen atom, it carries pair of electron. That pair of electron bonds with the carbonyl carbon. Here also cleavage of pi bond in between this carbonyl functional group. Oxygen atom gets negative here. Oxygen atom gets negative charge. This is another intermediate, but it is a unstable intermediate. It contains positive and negative charged species. From this, cleavage takes place immediately. How the cleavage takes place? Please observe. That negative charged electron shifted to this side immediately. Here, formation of 5 bonds on this particular center of the carbon. 5 bonds. It is not possible because that immediately this CN sigma bond cleavage takes place. Cleavage takes place and neutralize this particular heteroatom. Heteroatom, it gets positive charge because it is immediately neutralized and form a normal pyridine. Pyridine is here in this reaction we are using as a catalyst because that uh, in the starting it involves, it activates the reaction. In the final step we are getting same pyridine ring. In the final step we are getting same pyridine ring here. From this step we are getting pyridine and the remaining, please observe here, pi bond again form a pi bond R R O C double bond O and CH3 CH3. Here please observe, after breakage of this CN bond, the remaining structure please observe R O and C double bond O and CH3. This is the ester. This is the ester alcohols on reaction with the acyl chloride. Acyl chloride will get esters in presence of this particular pyridine as a nucleophilic catalyst. Pyridine as a nucleophilic catalyst. Okay. Now let us go to reduction reaction. I think it is the last chemical reaction for this pyridine. Reduction reaction. Reduction. Pyridine. Pyridine on reaction with the hydrogen. Reduction in presence of palladium charcoal. Palladium charcoal gives this saturated cyclic ring. Saturated cyclic ring. In presence of another type of catalyst, we'll get the same saturated cyclic ring. What is that? In presence of sodium metal and methanol. Here, methyl alcohol. It is a methyl alcohol or methanol. In presence of methanol or methyl alcohol with a sodium metal, reduction takes place. After reducing, we'll get in presence of both the catalysts. Reducing catalysts, we are getting same product. Same product. This is the saturated cyclic ring, saturated six-membered cyclic ring, saturated six-membered cyclic ring. Uh, this is called as piperidine. Piperidine. Pyridine on reaction with the hydrogen in presence of these particular catalysts will get piperidine. Piperidine is a purely saturated cyclic six-membered cyclic ring with heteroatom nitrogen. Piperidine. Is it clear? These are all uh, various chemical reactions of pyridine. Now let us go to applications of pyridine. Medicinal uses of pyridine. The first one, pyridine in anti-tubercular agent is used as an anti-tubercular agent. Isoniazid, in the formation of isoniazid. Here please observe in the structure. It contains pyridine cyclic ring. And next, it is used as antibacterial agent. Antibacterial agent for the preparation of these drugs. Please observe sulfapyridine and sulfasalazine. In this compound, it contains pyridine cyclic ring. And the next one, anticholinesterase agent, pyridostigmine, used in Myasthenia gravis. In this compound, it contains pyridine six-membered cyclic ring. Next, it is also used in proton pump inhibitor. These are the drugs preparation. All these compounds containing pyridine ring, used in omeprazole drug, omeprazole, uh, lansoprazole, and pantoprazole and rabiprazole. These are all used for peptic ulcer. Peptic ulcer. All these drugs containing with the pyridine cyclic ring. Pyridine cyclic ring. Here we are representing X, Y, Z substituents. X, Y, Z here we are giving in the tabular form different functional groups X, Y, Z. These are all different functional groups attached for this compound. And the last medicinal use based on this pyridine cyclic ring in vitamin B3 it is a nicotinic acid structure. Please observe pyridine ring containing compound nicotinamide. It is also pyridine containing compound in vitamin B3 and vitamin B6 pyridoxal phosphate. Pyridoxal phosphate. This vitamin B6 is also containing pyridine cyclic ring. These are all the medicinal uses for the uses with the pyridine cyclic ring. Okay, all the students, successfully we completed this heterocyclic compounds. First, we discussed about five-member classification, different heterocyclic classification, and various examples of five-membered cyclic rings, that is uh, pherol, furan, and thiophene compound preparations, aromatic characters, basic acidic characters, and different chemical properties, and each of the compound applications or medicinal uses we discussed successfully. Tomorrow we'll meet again in this at the same time with a new topic, another new topic. Today we completed this HCC heterocyclic compounds successfully. Thank you, one and all.